Good afternoon, and welcome to Hand-Wavy Chemistry, where we do not delight in the details, but rather bask in the big picture. Today, we're going to be considering the question, how big is an atom? Now, the very short answer is small, incredibly small. But could we possibly come up with a way to estimate it? Now, before we begin trying to make an estimate, let's consider some other options and possibilities, such as, is it possible that all atoms are exactly the same size? If we look at the periodic table, we will see that for every element mentioned, there is a set of numbers, one of which is called molar mass. Molar mass relates the mass of an element in grams to the number of atoms present. The exact number involved is called a mole. Like a dozen is 12, a gross is 144, a mole is approximately 6.022 times 10 to the 23, which is a very large number. Now, if all atoms are exactly the same size, then we should see a correlation between the molar mass and the density of a substance. So, if we consider carbon, carbon has a molar mass of approximately 12, and it has a density of about 2.26 grams per cubic centimeter. If we roughly double that molar mass, we find we have magnesium. Its molar mass is slightly over 24. However, its density is actually less than that of carbon. This immediately refutes the idea that all atoms are the same size. So, if they're not all the same size, how big are they, and how can we make that estimate? So to make this estimate, we need a few more concepts. The first comes to us courtesy of Avogadro. Avogadro had this idea that for a specific volume and pressure of gas, there will always be exactly the same number of molecules present. So, it doesn't matter if I were to fill this balloon dog with air, with pure oxygen, with nitrogen, with helium, or sulfur hexafluoride, it would take the exact same number of gas molecules to inflate it this much. The next idea we need comes from Boltzmann. Boltzmann was able to relate the temperature of a gas to its average kinetic energy. Now, to grossly oversimplify why this is important, when the gas molecules collide with the walls of their container, they bounce off, and this provides the pressure. So if we know what the average amount of energy the molecules have, then by relating this to the temperature and the pressure, we know roughly how many must be present. And this does give us a way to approximate that number for the mole, the 6.022 times 10 to the 23 I said earlier. So now that we have this idea relating to how much of a substance is present and its mass, we can start to make our estimate. Let's think about aluminium for this. The density of aluminium is 2.7 grams per cubic centimeter, or 2,700,000 grams per cubic meter. If we approximate each aluminium atom to be a cube, we can look at it and say, well, how many of these tiny little cubes are there inside our cubic meter of aluminium? So let's do a quick bit of maths. So we have about 100,000 moles of aluminium in our cubic meter. This means we have approximately 6 times 10 to the 28 atoms, multiplying the number of moles by 6 times 10 to the 23. We're assuming that each atom is a tiny little cube, so therefore each of these cubes must have a volume of 1.667 times 10 to the negative 29 cubic meters. Taking the cube root, we find that each edge of our atomic cube must be 2.55 times 10 to the negative 10, or about 2.5 angstroms. Now, the official diameter of aluminium is 2.36 angstroms. So we're in about the right ballpark, even though we made a very crude assumption. Now, I mentioned there that there is an official diameter for an aluminium atom, and you may be wondering where that number comes from. Nowadays, we have techniques like X-ray crystallography, which lets us create images of atoms and molecules. So one way that we can approximate the size of an atom is to look at the distance between two nuclei and saying, well, if the distance is this, cut it in half, there is our atomic radius. But what we do start to see is that the size of the atoms, or the distance between those nuclei, depends on what they are, what kind of bonds are there, and how it is that the molecules are interacting. But that is a story for another time. I hope you have enjoyed this video, and if you have, please do make sure to click like and subscribe. And if there's anything you'd like to discuss, either about what you've just seen or as a possible future topic, please put it in the comments below.